bring on some more functions, and I think as we, of course, make it maths, I think it's time to hit these beloved logs and logarithms that have been threatening to come into our lives, and here they are, welcome. So, if you're worried, I think that's a backlog, right? No. So, logarithms. Now, the starting point for logarithms is exponentials, and we're going to rewind to sequences and series where we had something like 2 to the n equals 1024. So when we were given this originally, what we said was, well, we're kind of just going to guess or do some trial and error and go, well, let's try some numbers. N equals 9, it was too small, 11 was too big, and we ended up with, cool, n equals 10, 2 to the 10 equals 1024. But that's really tedious, and it only works if these are nice integers. What happens if 2 to the n equals 1025? 10's going to be too small, 11's going to be too big. What are we going to keep guessing? 10, 0, 0, what? No. Okay. So logs to the rescue. So logs basically allow us to do this. We're going to take the log of this number, 1024. Our base stays the same. So our base is 2. So our base is 2. So what we're saying here is that if we take the log with a base of 2 of 1024, if we take this, what we get to do is have our exponent as the subject of the formula. Mind blown, right? So we got this. If we took the log of this number with the same base of 2 as we had, then we can get our answer of n. And if you grab your calculator out and you go log base 2 of 1024 equals, let's do that. So let me grab my calculator. So where I was getting my calculator, right? So there it is, calculator to the rescue. So on the calculator, if you've got one like this, and the silver version similar, and all the calculators similar, there's a log button up here. So this log button says we get to choose our base. I'm going to choose the base as 2, right, of 1024. Hit equals and just see the magic. Okay, magic, right? 10. And it is quite something. Like before we're just trying some numbers. Now we have a good method to find it. So let's maybe run through some examples of how this works. So I'm going to write these down as we go, and we don't need the calculator in our way just yet. So we've got, for example, 1. There are going to be a few of them. If I tell you that 2 to the 3 equals 8, how are we going to write this in log form? So in log form, I said that we want to, log is our new function. It's the inverse of the exponential. And there are 2 parts to this. 1, the whole point of logs is that we want the exponent to kind of come down here to be the subject of the formula. So our exponent is now the subject of the formula. And the base was 2 here, and the base stays the same. So if we take the log of base 2 of 8, we'll get 3. So let's pop our calculator up and just kind of confirm that seems to work. So the log base 2 of 8 gives us 3. Okay, so how are we going to remember how to do all of these things? So the one way to think about it, which I think works for me, is we're taking the log, the base still stays the same, must stay the same. Like think exponents, whereas like the base must stay the same. So the base stays the same. The whole purpose of logs, or not the whole purpose, but one of the main purposes is that our exponent becomes the subject of the formula. So 3 becomes 3. So we've got 8. So the log of 8 with a base of 2 is 3, or log base 2 of 8 is 3. Second way to maybe just remember it is if we've got our exponents on the left and we have our logs that way, you go left, right, left. So this 2 is on the far left, so that goes there. Then we went to the right, which is over there, and then went to the left, which is there. Kind of works. I really like the more conceptual first one. Okay, so let's do some more examples here, just to kind of get into our logs and converting between. So second example I've got is, well, if we're given 4 squared equals 16, indeed it does, convert that into log format. Okay, so we got log, We know the point is to get the exponent down to be the subject, and the base stays the same. Not really much left to do. That must be 16. Okay, let's do another example. Let's kind of keep them all around together here. So if we've got 10 cubed is 1,000. Remember that little trick of like the 3 zeros or something. So here, write it in log form. Okay, so we're writing log. Purpose was to get the exponent to be the subject, and therefore the base stays the same as 10. So the log base 10 of 1,000 is 3. Now often you'll see this written just like this. Now normally we work in base 10. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's when it goes from 1 digit to 2. So logs, if we don't write a base, then our base is implied as 10. Okay, let's do another one. Why not? And for our next trick, we're going to say, okay, what about, okay, let's do one more like this to go log, not log. Oh, yeah, why not? So the log base 3 of 9 is 2, I'm telling you. Now convert that to exponential form. So the opposite direction we're just doing. Okay, so you could think, okay, the base must stay the same. So this was 3 was our base, so 3 is our base. Now, going from exponents to logs, we got the exponent to be the subject. So now the 2 must be our exponent. And so 3 squared equals 9. Maybe this one kind of thinks of a left, right, left. Maybe that makes more sense here. 3 squared is 9. Left, right, left. Feels like some sort of military parade. So left, right, left, left, right, left. But base stays the same as one that's always going to stick. Base must be 3, base must be 3. 3 squared is 9. Okay, let's just going through these gently so that we can get into them. And go, what about, let's do one more like that. The log base 2 of 5, the log base 2 of 32 is 5. So rewrite this in exponential form. Well, the base stays the same, 2 to the 5 equals 32. Now, I'm a big fan of just make sure the log or the exponent part's on the left-hand side. Then we just keep the same flow going. So if you were given 5 equals log 2 32, at least to start with, just rewrite it as log base 2 32 equals 5, and then you can go 2 to the 5 equals 32. That's an awful 5. 2 to the 5 equals 32. So just rewrite that as we get into these. Okay, so let's see if this can help us maybe solve some equations, which of course it can. So let's say we say that the log base x of 8 is 3. And I ask you, determine x. Okay, so x base stays the same. Cubed equals 8. Oh, well, that wasn't too bad. Cube root of 8 is 2. Let's do another one. And this next one, I think, is going to be a bit more fun, surely. This one here is the log of base 5 of x is -1. Okay, so 5 -1 x. Okay, yeah, we're there. 5 -1 is x. Okay, well, 5 to the -1 is a fifth equals x. So we can have fractions and think things are going to be like increasing and decreasing and all sorts of things as well when we get to the bases, but that's what we're going to get to. So let's get down a nice formal definition of logs before we do one final example. So more formally. Logs. Sounds like a bad, I don't know. So logs. If we take the log of something with base a, and remember notice I'm writing, that's kind of subscript x, but the x is on the same level as log, equals y. What that means is that a to the power of y equals x. and vice versa. So if we're given a to the y equals x, then log base a x equals y. Now when we did exponents, this base here, we never had a negative number. So we always said a was always greater than 0. But also we never had 1, because we wouldn't have like 1 to the power of 7 or y equals 1 to the x, because 1 to the power of anything is always 1. So a is also not going to be 1. Or not 1, what am I saying? A is not equal to 1. And finally, when we drew our exponential graph, remember when we drew our exponential and we had a positive, we said, oh, it goes like that. We never had a negative y value. So this y value is negative. So in this case, for our log graph, remember our log graph, well, not remember, it's going to be our inverse. So we're never going to have a negative x value. So x is always going to be positive. So this part over here is always going to be positive. It's going to be x is always going to be greater than 0. Okay, let's do one example. One final one that looks more complicated. Solve. Go for it. The log of base 2 of x squared plus 2x equals 3. Solve. Okay, so let's go through it. Here we've got 2 is our base, so 2 is our base. 2 to the 3 equals x squared plus 2x. Okay, feels like we've got some more work to do. 2 cubed is 8, x squared plus 2x. How do we solve quadratics again? Oh yeah, we just go x squared plus 2x. Let's subtract 8 from each side, so we've got a 0 there, because then we can use our trick of going, well, factorize, and we've got x and x. Got it. Okay, so we got minus 8, so we got plus 4 minus 2. So x equals negative 4, or x equals 2. Now wait a second, didn't I just say that x cannot be 0, not be negative? Look, here it is here. X must always be positive. So we can only take the log of a positive number. Okay, but let's try both of these and see what works. So the log base 2 of, let's start with our 2 and see where it gets us. 2 squared, 4. 2 times 2, so we're going here. 2 squared plus 2 times 2. Well, that's the log of 4 plus 4, 8. Well, what is log base 2 of 8? Go and work it out. Oh, right. It's still in our calculator. It's what we did earlier. So this does indeed equal 3, so we're good. Let's try the other option. And this is our parting shot. So here we've got the log base 2 of negative 4 squared plus 2 times negative 4 equals log base 2. Well, negative 4 is 16. 16 plus minus 8. 16 minus 8. Well, that's 8. Hey, that seems to work. So it does work, because we're still taking the log of a positive number. So therefore that's fine as a solution. Okay, so the exercise for today is just about converting between logs and exponential and logs, solving simple equations based on that. So that's what today's one. Tomorrow we're going to hit log laws. So while we're thinking of doing that, of course you need to make it math.